Okay, welcome back. So I left you with this conundrum of if you were using this equation to find the distance to an object, so you knew the absolute magnitude perhaps from the spectrum, and what would be the error if you ignored the fact that there might be dust extinction along the line of sight. So in this case, so I'd assume you've got one magnitude of visual extinction here as AV. So if you let's do it in log D since we're only after the factor. So if you make that the subject, then you get this equation. So this is what you should use if you're considering the dust extinction. And obviously if you don't have that, if you're ignoring that dust extinction, then this is the equation you would have. So the difference between the two is the sort of error you're going to get on the distance, if you like. So D primed here is the wrong distance that you would get if you ignore the dust extinction. So just subtract the 2 here and everything drops out apart from this AV over 5 factor, and we're taking AV to be 1, so that's a fifth, and that's in the log. Okay, so it's the difference of 2 logs, which is the ratio of log of the wrong distance over the correct distance. So you can solve that for the ratio of the incorrect distance to the true distance. And you can see it's quite large, right? 60% bigger if you ignored just one magnitude of extinction. Okay. So you can see that if you get the distance wrong, then that comes into the luminosity by d squared. So you can get all sorts of problems if you ignore dust extinction. And it's a real problem. Here's a view of the whole Milky Way in the optical. We're going to come on to that in the next lecture, I think. So this is a picture of our galaxy as we see it from within it, and you can see that there are these dark dust lanes throughout especially the plane of the galaxy, the Milky Way. And so whichever direction you look in, you've got problems with dust extinction. Okay, but there's another property of the effects of the interstellar dust, which is to not only dim your objects, but also to change their color. And this usually actually helps us a bit. So the reason for this is that, as you can imagine, the amount of extinction that a population of dust grains cause is not the same at all wavelengths. It varies with wavelength. And in particular, especially certainly throughout the optical regime, the extinction is larger at blue wavelengths than it is at red wavelengths. So if we want to express that using this total extinction measure, we can label this with the different filters. So the extinction in the blue filter, for instance, would be larger than the extinction in the V filter. So, as I just said, this means that interstellar dust along the line of sight between us and our target object causes them to appear redder than they really would be, as well as getting dimmer, okay, so less bright. So this is referred to as interstellar reddening. Okay. So here's a sort of a nice image that illustrates that effect. So what you've got here is a sort of background of stars in the Milky Way, sort of through the plane of the galaxy, and in front of it here, or between us and most of these background stars, is a cloud of interstellar material. So there would be interstellar gas in here. So this is a cold, sort of dense cloud. So this would be actually molecular gas in here mostly, and mixed in with it are the dust grains. So this is not a hole in space. On the contrary, there's actually sort of dense cold gas and dust here, and it's the dust that is doing the extinguishing of all the background light. So in the middle here, you can't see a thing. Okay, so that's extinction, right? And then you literally can't see any of the background stars because it's made them so faint you can't detect them. But if you look around the edges, where we're sort of just seeing through the lower density parts around the edge of the cloud, you can see the reddening effect. Okay, so here you can start to see some stars towards the edge of the cloud, but they all appear much redder. This is an image from 3 combined filters, the B, the V, and the I, so just off the end of the optical. And so you can see that the stars here appear very red, whereas in reality, they will have the same sort of distribution of more sort of bluey, orangey colors that all of these background stars have. But the dust is making them appear red, and that's because it's preferentially absorbing more of the blue light than it is of the red light. We'll come back to that image later. Here's another sort of rather famous object. It's referred to as the Horsehead Nebula. It's sort of in the Orion region. So here the background is actually mostly nebula light, okay, from the various sort of H2 regions in the Orion region. But again, there's a dark dust cloud in front of it here, which is blocking all of this nebula light here. There are a few stars again attempting to shine through, but again, they appear much redder than the ones that you can see that are not going through the dust cloud. Okay, so we can also quantify this reddening effect in a very similar way to the extinction effect. Okay, and here we come back to the idea of using the difference between 2 magnitudes of the same object in 2 different filters as a way of measuring the color of an object. Okay, and we can define this new term here, which is referred to as the color excess. Okay, so this is normally referred to as E, B minus V, so it's E for an excess color, and B minus V tells us which color we're talking about. And in the same way as the extinction, it's defined as the observed color. Okay, so this is what you would actually measure with your telescope, minus the intrinsic color, which is the color that the star should have, or does have at source before it goes through any dust clouds. Okay, so it's always this way around, observed minus intrinsic. And again, just as before, you can see that this is going to be a positive quantity because the dust is only going to make an object redder. And if you recall, a more positive B minus V value means that the color is redder. So the observed color will always be redder than the intrinsic color, and hence this value will always be positive. So that's referred to as the color excess. So that is a way of quantifying the reddening effect. Okay, so let's look a little bit more closely at how the extinction varies with wavelength. So this is invariably called an extinction law, even though it's a totally empirically derived sort of curve, and it's not really a law at all, but that's the name that it's given. So basically the extinction law is just how, if you plot a lambda as a function of wavelength, then that's the extinction law. I'll show you a diagram in a moment. But a nice relationship that comes out of the idea that there is a fairly sort of universal extinction law as to how the extinction varies with wavelength, allows us to relate these 2 quantities. Okay, so that AV is about 3 times EB minus V. And that's because the dust out there in the interstellar medium is fairly sort of uniform in its composition and size distribution, etc. So no matter where in the galaxy you look, which line of sight, the extinction law is fairly similar everywhere, at least certainly in our galaxy, to a reasonable approximation. And this is an approximation here. But this allows us to use this relationship, and it's, as we shall see, it's actually quite handy. And the reason for that is if we can get a handle on what we think the intrinsic color of a source is, for instance, if you've got a star and you can take the spectrum. Okay, so you can then spectral type that object, and therefore you can, which tells us about its effective temperature. And as you know from earlier in the module, the color, intrinsic color of a star and its spectral type are very closely related. They're both proxies for the effective temperature. So therefore we can use the spectral type to get to the intrinsic B minus V, and obviously we can observe the observed B minus V, so that would give you the color excess. And then we can use this relationship to work out the total extinction at any particular waveband. And therefore we can then correct the observed magnitudes for the extinction effect through the use of the reddening effect. And you might think, well, you know, if you've got the spectral type of a star, then you know its absolute magnitude, so surely you can correct AV that way. I mean, in principle you can, but there's a lot more uncertainties in translating a spectral type into an absolute magnitude. Again, if you go back and look at the sort of tables that we've had in the workshop, a small change in spectral type gives a very large change in absolute magnitude for many different types of star. So that can be very problematic and error-ridden, whereas the color varies sort of slowly and smoothly with spectral type, and this is a much more accurate way of getting to the extinction. So that's usually the way that it's used. Okay. So here's an example graph of this so-called extinction law. As you can see, it's just a purely empirical curve that's derived from observations. So it's not a law at all. Okay, but it gives you the idea. So this is the relative extinction. It's plotted in a kind of unusual way. So it's got wavelength here on, but it's kind of going backwards. So V and B are the other way around here. Okay, so this is the sort of visual part of the spectrum, and here we're off into the ultraviolet part of the spectrum, and here we're over in the infrared part of the spectrum. But the idea here is that that relationship between AV and EB minus V is really just the slope here. Okay, so that's where that factor of 3 comes from. Okay, and like I say, this sort of extinction law is fairly uniform throughout the galaxy. So wherever we look, you will see there are some sort of bumps and wiggles in here, some features. Okay, just out of interest, again, it's not part of the assessed bit of the module, but this is how we know what the dust is made of. So this bump here in the ultraviolet is due to grains made of sort of carbonaceous materials, so carbon-rich material. If you took a sort of reflected spectrum of the graphite in your pencil, you would see a feature at around about this wavelength as well. So that tells us that some of the grains out there are made of carbon-rich material. There are other features further down here in the infrared that tell us that other grains are made of the silicon material. So these are broadband spectral features in the extinction curve that tell us what the dust is made of. Okay, so here's an example for you to put this into action. Okay, so star has been spectral typed, and it's had an estimate of its absolute magnitude and its intrinsic color, and it's got an observed apparent magnitude of this, and its observed color is plus 0.4. So you can see that the reddening effect has changed its intrinsic color from minus 0.1 up to plus 0.4. And so the question here is, how far away is it? Okay, so have a go at that, and you'll see how this works in practice. We'll come back after the break.